morning lab is going to be on RosettaScripts. And I really do like this lab and the next lab I get to give you guys because it's all about kind of making your life easier. So hopefully you like me a bit more. Anyway, so just to sort of like contrast RosettaScripts versus, just sort of like normal Rosetta. So with C++, you have to recompile after any change you do. A lot of the options you have to give as command line arguments, and I feel like a lot of the the applications sort of feel like a black box, and especially some of the errors can feel especially arcane. And in contrast to XML, there's no recompilation needed. A lot of the options you can instead pass as a tag attribute, and it's a lot more transparent or easy to kind of like do what you want to do with RosettaScripts. Okay, so this is sort of a skeleton of a sort of standard RosettaScripts. So XML stands for Extensible Markup Language, and so you use tags with the caret keys, which is similar to HTML if you guys are familiar with that. And then anything outside of it is just a comment, and so it's really easy to comment these. And then also these tags can be nested with like tabs to represent hierarchical data, and we'll see how that looks a couple slides. There is a blank RosettaScripts template that's available at this link, and sort of just gives you like a blank one that you can use. And then there's also you can make a blank template with the following command. So just the RosettaScripts executable to make sort of like a blank XML for you to fill in. To actually run your Rosetta script, you're going to use again, the RosettaScripts executable, and just pass your XML to it, and then any sort of like PDBs or anything like that you want to pass to it. Okay, so we're going to kind of go over all of these different parts of a Rosetta script and like how to use them and what they do and all that sort of thing. So starting with the score function. So we do need a score function because that's how we're going to be minimizing like our pose and all those sort of things. And so for movers, you can set a score function attribute. And score functions have two components, terms and weights. You can use keywords to sort of like preload a like known score function like ref15 or centroid. You can also use your own weights file, or you can take an existing score function and sort of reweight it or tailor make it to whatever you need it to. So for example, this is just sort of loading in like the normal ref15 score function. And then with the centroid score function, you can, for example, set like the van der Waals term to 0. So you can either sort of use like the preloaded score functions or change whatever you need to make it work. Okay, so moving on to movers. So movers are things that alter the pose. There are two common subtypes, the packer and the minimizer. We've talked about this before. Just to go over it again, packer substitutes amino acids and rotamers for sampling, and then the minimizer just minimizes the backbone and sidechain torsion angles. Here's some documentation on the movers you can use, and for just an example, in this case, this is the min mover and the pack rotamers mover. Okay, so how do we sort of like fine tune the movers to do exactly what we want them to do? So that's with attributes. So attributes will alter the mover behavior. There is documentation for each mover, the sort of like different ways that you can fine tune things. But in general, the default values are sort of a good place to start, or at least see how it works. So for example, this is the min mover. You can have the score function, chi and backbone, weights, and then the Cartesian, using Cartesian versus like torsion angles. So an example, you can see two different ways of like sort of implementing a mover. So in this case, we're using ref15 Cartesian coordinates versus ref15 sidechains. And then setting the weights, for example, like the sidechains versus the backbone angles, and then using like Cartesian coordinates versus torsion angles, et cetera, et cetera, et cetera. Subtags let us handle more complex behavior. And so, for example, the move map lets us sort of like define behavior for subsets of residues. And so this is an example of one of those. And so, for example, if we have our move map, and this is something I want to ask you guys what exactly this is going to do. So we have three different sort of like conditions that are being applied for our residues. So if we have residues like 1 to 99, can anyone read this and tell me sort of like what's being done to this pose? Like what's being turned off, what's being selected on? If residues 1 to 99, the backbone is turned off, and so are the side chains. So we're starting with nothing happens. Okay, so then we go back to 1 to 50, and we're allowing what to move with these? Yeah, basically like everything, right? So the chi-angles and the backbone. And there's one more rule that is applied after that. Can anyone tell me what this does?
Turns off the triangles for 5 to 10.
Yeah, sorry, Bill, I just saw your hand. Exactly, yeah. So for 1 to 50, we have, sort of the chi-angles and the backbone angles can move, but for 5 to 10, only the backbone angles are allowed to be moved. So yep, so there's it's like Boolean logic, like if and or. For a lot of these things, you can sort of like apply multiple conditions to get exactly what you want. Okay, so moving on to the packer. So we can control it with task operations. And this is going to control like how the designing or the repacking parts of the packer works. So this is a really important one, restrict to repacking. So this disables the design part of the packer and only allows for sort of like the repacking element of it. Prevent repacking. This disables any changes in the sidechain conformation. And then extra rotamers generic allows for additional rotamer sampling. And it'll give you like a better solution, but it'll take a little bit longer. And so that's what these look like in the actual task operations. Restrict to repacking, prevent repacking, then extra rotamers generic. Okay, so specifying residue subsets with residue selectors. So this will give you a subset based off of selection criteria, and there are confirmation independent and confirmation dependent residue selectors that you can use. And yeah, you can pass, these are passed as inputs to other Rosetta modules, movers, filters, task operations, other residue selectors. So you can use these in the other parts of this to sort of like get a subset of residues that you want to use exactly. And then here's the documentation for a list of available residue selectors. But to go over some of the examples, so for example, if I just want to get all of the alanines, so sort of go by residue identity, you can do that by just giving like the 3-letter code and also select all the alanines within the pose. You can go just by numbers, so resnums 1, 10, 20. It'll just select 1, 10, 20. You can also give it a range as well to sort of like get like 1 through 10, 10 through 20. And then you can also go by chains, so A or B. And this is what they actually look like in the actual XML. Okay, so just beyond sort of like maybe the normal selectors, you can also do some really cool stuff with like confirmation dependent selectors. So for example, you can select residues based off of how buried they are. So that'd be select core equals true. So you're wanting stuff in the core of it. You don't want something on the surface. And so you can use, SASA to select that. And you can also select by secondary structure. So in this case, this is selecting all the helices. And you can use, for example, you can use like DSSP to determine the secondary structure in your pose to select on. And once again, this is how it looks in the actual XML. You can use Boolean logic. I know I said that earlier, but you can use Boolean logic for any of these residue selectors. And so, for example, if you want to do not residue selector, it'll be all the residues that are not RS1, and or, and these are sort of how they look. So they have to be, and is like all residues that are both 1 and 2, and then or is, 1 or 2. Okay. Filters. So yeah, this is really important. So because sampling is stochastic, sometimes it might be sort of going in the wrong direction. And filters are how you can sort of like kill the job early and have it restart to avoid just sort of like going down the wrong rabbit hole unnecessarily. So for example, if we want to repack all the surface residues, but we want to maintain a key salt bridge, you can tell Rosetta to automatically rerun a failed job using the job distributor 2 option. And you can specify the amount of times each attempt is allowed to retry if it fails. So for example, the filter is just the atomic distance for this salt bridge. So you're specifying 2 residues, and you're just giving a distance cutoff where if it goes beyond that distance, the filter will be applied and it'll restart it. You can also use filters to evaluate pose metrics, for example, SASA, RMSD, et cetera, et cetera, et cetera. You can put these at the end of the filters are always put at the end of the protocol section. And then the results of the filter will be placed in a column of the score file, as you can see if the filter was applied or not. And so, for example, you can do, for example, sidechain RMSD to see if it, check how close it is to what you're trying to evaluate it on. Okay, so protocols. So protocols is the part where you're sort of like doing the actual thing. This is almost kind of like a main function, if you guys want to think about it that way. So this is sort of where you actually tell your Rosetta scripts to do the thing. The important thing about this is that order matters. So it's non-commutative. So you have to make sure that you're putting it in the order that you actually want things to be applied on. So, don't put your filters at the beginning. It'll not go the way you think it will. Okay, and then the last thing is output. So you can modify the output tag to, for example, use a different score function at the end after you're finished applying the entire protocol for your Rosetta script. And generally, this will define the score function that will be used for the score file output that you get at the end. And if you don't want to specify anything, then the sort of like command line score function is what it's going to be using. And so, for example, the output score function here is, for example, like centroid. Okay, so now that we've built our Rosetta script, how do we run it? So there is a Rosetta scripts executable, and that'll just be parsing all of the Rosetta scripts. So it's actually pretty easy because you can always just use Rosetta scripts and then just give it the XML you want it to use. Yeah, so invalid XML files and any missing options that are required to run it will cause it to crash. And then also, Rosetta Scripts does allow for like job distribution. So any JD2 options are compatible with Rosetta Scripts as well, for example, and trials. This is sort of like the additional documentation. If you have any questions about like what Rosetta Scripts can do and like different movers and filters, this is a place to go to sort of like read up on all those things. Okay, so now on to what we're actually going to be doing with this lab. You are going to be making a Rosetta script. So first you're going to make a small mover, and it's just going to do some Monte Carlo sampling of backbone torsions. And then you're going to use the pack rotamers mover. And so you're going to restrict to just repacking, so there's no design element. And then you're going to use the residue selector to sort of select just a helix to repack. You're going to minimize it and then filter by score. Yeah, and that is it on that. So go forth and enjoy Rosetta Scripts.